guess I'll introduce myself. I'm David Wirth. I'm the inventor of the first portable railgun. And today I'm going to talk about additive manufacturing, a catalyst for innovation, and railguns. This is actually kind of part of a formal presentation that I gave a little while ago, and we can kind of take this wherever anyone wants to go. If anyone has questions, just speak up and try to hit them. But I'm basically going to go over how I made this thing, how it works, the various additive manufacturing stuff I had to look into to make this whole design work, and just hitting anything you guys have. So a brief history of some of the stuff I've done is my interest in railguns actually started back in high school. I made a little, physics, demo out of a couple disposable flash cameras and some little pieces of copper and a flash charging circuit and some AA batteries, and it shot a little piece of aluminum foil out, and that was my first railgun, I guess. And this thing probably won't play, but if you click it, it should play the video of, yeah, there we go. So yeah, you can see it shot a little piece of aluminum foil and knocked a piece of paper over. And that was off of a AA battery and about 9 joules of energy. So, did that. I did some other projects. I did a little inductive charging thing so you can charge your phone while you're driving. I made some of the first LED headlights for a car using this weird thermal management system. I also made some little art projects, compressor mirrors, stuff like that. I also made a rocket engine for Discovery Channel, as well as some composite materials I developed for one of their shows. They were making a manned portable bunker. And I also did some stuff in the Naval Postgraduate School. I made a wireless mesh network that was wearable. So essentially it had a computer in there, and it would monitor your heart rate, your body temperature, and a bunch of other stuff, and it created this wireless mesh network, and so you could transmit your vital signs to other people wirelessly, even when there was no cell coverage, no radio signals, nothing, because it was extremely low bandwidth. And came up with that, and also a wearable battery. It uses electroconductive Velcro, and so essentially all you do is you take the battery, you slap it on wherever the terminal is with this electroconductive Velcro, and it just runs. So I came up with that. I also did some work for AFRL on novel solid rocket propellants. So essentially what I did was we took some nanoparticles that reacted with light, and we used that to make one of the first restartable solid rockets. So it's actually a solid rocket that you can start, you can stop it, and then you can start it up again. There's actually a video if you want to click that little VLC button. Yeah, the little cone. Up.
3, 2, 1. Somewhere.
It's brought it up, it's just not part of the presentation.
Oh, okay.
Cells, full pack.
Yeah, so, yeah, there was a video of the thing firing multiple times. But yeah. So, actually, this railgun project started over a beer bet and a game of Halo. And I forget if it was Halo or Modern Warfare or whatever. There was some game, me and some guys were playing, and they had a railgun in this game, and I was kicking everybody's butt with it. And a couple people knew about my high school railgun project, and they said, well, I bet you could make a real railgun. I go, really? Is that a bet? I'm like, yeah, it's a bet. And so I'm like, okay, we'll see. And turns out, yeah, I made a real railgun. It's not quite as good as the Halo one, but yeah. So let's see. I think you might have to minimize the presentation after you click it. Oh, there it is. Kind of over.
I see it's got
Yeah. Yeah, there we go. Yeah, okay. So that's not me, that's the Navy. That's what I'm doing. Fire aluminum, graphite. I actually did tests with iron, tungsten, and non-conductive materials like Teflon, so it can fire anything. I can even push it. Let's just repeat it. Yeah. Yep. Okay. So I'm not going to go into the math, but I'll explain how it works. Essentially, what you have, and this is the new version of the thing. So, I apologize for it not being exactly what you saw in the video, but essentially what you have is you have two parallel rails. And you have two parallel rails, and you run a current between them. And that current creates a magnetic field. And the interaction between the magnetic field and the current running through the rails and through the projectile creates a force. It's called the Lorentz force. And it accelerates the projectile pretty much as fast as you want to go, because there's no limit on how much energy you can put into this. It's just how much energy you have stored electrically. So the Navy, in their designs, what they did was they had as much energy storage as they ever wanted. They could put a ship's worth of energy into this thing. But for a portable design, it's all about efficiency. It's all about getting the most bang for your buck. You only have a certain amount of energy you can store based on the efficiency of your capacitors. So you need to figure out a way to get the most force out of that specific packet of energy. And so the way you do that is you augment the field. So instead of having just the rails creating the magnetic field, what you have is you have an external magnetic field. So here you have 4 magnets. And essentially what this does is it creates a linear B field around the rails, and that allows you to get a much more efficient rail design. That allows you to make a portable railgun. So how I started this thing was I submitted a white paper, because originally I was like, I'm not going to do this just on my own. I'm going to ask for funding and see what was going on. So I submitted a white paper. I said, here's how I'm going to build it. Here's what I want to do. And if you look at kind of how it developed, it actually worked pretty well. It came out pretty close to how I thought it would work. So I'm not going to go too much into that. But the people I submitted the white paper to said, no, we're not really interested. We don't think you're going to be able to do it. So I was like, all right, I'll try it anyway. So here's actually what I made, and here's how it works. So I'm going to talk about the rails. This took me about 6 months to get it right. It took me 6 months to figure out how to make just this part. So very difficult. And I originally went with a 12-inch rail because I was like, all right, bigger is better. Longer rails, all right, what's cooler? But no, that's not how you do it. You have to match the length of the rails to the amount of energy you have stored. So, and I also found out manufacturability is a big problem. You can't just machine, stuff into any shape you want. You have to think about how you're going to manufacture it. So originally I wanted to go with a circular thing, and it turned into a square because I couldn't figure out how to do a circle. But eventually I got it to work. And I found out a lot of ways that it didn't work, especially duct taping a thing on the lathe and trying to turn down a thing tied together with duct tape. It's not good for lathes. So this is how it eventually came out. I got the rails working, and then I wrapped it with carbon fiber to reinforce it so these things didn't fly apart as soon as I fired it. And then I put all this thing into a big Garolite tube, big fiberglass tube, and that created the bolt loading system. And the way you get the energy in, at least in the first version, was you have these big pneumatic connectors. They're just brass pneumatic connectors, and they conduct electricity really well. And they form a really, really tight connection with whatever conductors you're using. So the electronics, this also took me about 6 months to figure out how to do this. And I'm not an electrical engineer, so it's kind of messy. Yeah, I'm not good at electronics, and I shocked myself a couple times doing this. But eventually I figured out how to do it. Essentially how this version worked was I had a 12-volt battery. It was just a 3S LiPo battery like you use in an RC car, and I ran that through a little mini inverter. like something you use in your RV, but really tiny. And then I took that mini inverter and I ran it through a CRT transformer. You know, it's not a fly, it was like a really old CRT transformer. Stepped up to 1500 volts, and then rectified that, and you feed that rectified voltage into the capacitors, and that charges it. It's not, I mean, that was the best I could come up with. So energy storage, this was another big challenge. Didn't take me quite as long to figure this one out, but essentially there's only so much energy storage you can hold. You know, you're limited by weight in this case. So I had to figure out a way to get 6 big, huge blue capacitors into something portable, and I used 3D printing to do that. Made this little holder, and I made some flexible bus bars, and I made sure all the wire gauges matched up, and this is what came out of it. And this little guy, this little section up there is actually emergency discharge, SCR. What that does is if something goes wrong and the thing doesn't fire, and you're left with a fully charged capacitor bank that you don't really want to be holding, press that little button, and it dumps all that energy into a resistor. And so it makes it safe again. And so the structure, this is actually the part that was most interesting, because you know, when I first posted this online, everybody said, oh, 3D printed, you know, it's not really 3D printed, you use a mill and a lathe, and you know, that's whatever. But really, there was no way for me to make this portable without a 3D printed structure. Me, because you could do it without 3D printing, but to do it cheaply and to do the number of revisions that I had to do, there's no way you could have done this on a hobbyist budget without a 3D printer. There's just no way. So you came up with a CAD file, and to get that CAD file to a printed object, I had to come up with a number of new techniques. So I kind of did this on a budget, and I didn't have a heated chamber. And if you're going to print ABS parts, you kind of need a heated chamber. So the way I got around that was I took some insulation and I wrapped it around the part as it was printing to keep it warm, so it didn't crack. And that worked. That worked actually pretty well. Then essentially, I also needed to print some very weird geometries that didn't like to stick to the build plate very well. So, did some research, found out PEI, polyethylamide, is a type of build plate that works really well. It makes plastics really stick to it. And so I went out and got one of those, and it worked. That's how I was able to print complicated geometries without a heated chamber. And finally, I 3D printed my own mini milling machine. So I didn't have to use a milling machine as much. And lastly, another thing I figured out how to do was I figured out how to use multiple spools to make these parts, multiple spools of filament. Because some parts use more than one spool of filament. And 3D printers, they don't like to pause. They don't like to pause. They don't do it very well, just because of the way the software works. And so, if I wanted to use multiple spools, what I did was I would make the infill small enough, and while this thing was printing the infill, I would quickly swap out the spools so it wouldn't lose a whole lot of strength. And that worked fairly well. So some lessons learned about the 3D printing aspect. Should have a standard fastener template. Standard template for how many fasteners you're going to use. Part clearances, and then some general stuff about additive manufacturing. So standard fastener template, for the whole design, I only used 4 types of fasteners. And you can make it work if you have a standard fastener template. I'm not going to go too much into that. But for using screws and bolts and other stuff in 3D printed parts, what you want to do is you want to have proper clearances. And SolidWorks doesn't do this very well. That's why I used Rhino to do this, because you can do these clearances really easily. And if you just have a hole that's as big as the part you want to put in there, it's not going to work. It's going to scrape against the sides. So what you want to do is if you have 2 parts that are mating, such as on this thing there's some holes, and on this thing there's some dowels. If you want to mate these 2 parts together, you have to make sure you oversize one and undersize the other so they fit, because otherwise it won't go in. So what I found was it's essentially you just want to have the nozzle diameter some multiple of the nozzle diameter to get you the right clearances. So I used the nozzle diameter for a loose fit and half a nozzle diameter for a tight fit. And I'm not going to go too much into this, but this essentially just highlights the benefits additive manufacturing gives you as far as regular manufacturing. And then here's some of the materials I used. Nylon, polycarbonate. I printed a few parts, but only for specialized stuff. Then it was mostly ABS and PLA. And fastener selection, I'm not going to go too much into this. And this is some stuff kind of about where I think the future of additive manufacturing is going. So I can go into that, or if you guys have any questions, feel free. Yeah.
What was the weight of the working prototype that we saw in the video?
That weighed 45 pounds. Yeah. So it was not light. Anybody else?
Did I also see there was like a CO2 or a gas canister? What's that? What's the purpose of that?
Yep. So what that does is when you make a railgun, essentially what you're doing is you're passing thousands of amps through a very small part. And when you pass thousands of amps through something, it wants to weld. And if that thing is not moving, it's going to weld in place. And so you need to give the armature, the projectile, some initial velocity before it gets that amperage. If you don't, it's going to weld. So the CO2 is to give it that initial velocity before it enters the rails.
You're building more rail guns or prototypes, or where are you going with all this?
So this is kind of just, a pet project, just a tinkering thing. It's not my full-time job. I am working on a version 2 just because I think it's interesting, and I think there's advancements that you could make to the design to make it more interesting. But yeah, I'm just kind of playing it by ear. So.
Could you have an outer shell, cover it, make it look like it's actually a railgun or something?
Yeah, that was essentially what I was going for in that design. I didn't do it very well, but that was kind of what the 3D printing was about. You have all the components on the inside, and then you have the shell that both holds them together and makes it look aesthetically like what we're looking for on the inside. But yeah, I guess I didn't do it very well.
So how many shots could you get out of it?
So there's 2 limiting factors for the number of shots you can fire. One is the capacity of the battery, the electrical capacity, and the other is the CO2. So the CO2 you can probably get 20, 30 shots out of a bottle. The electrical you can get 3 shots out of my last design. This new design you're probably going to get about 80 shots out of the electrical. There's also charging issues, so you can only pull so many amps out of the battery, and by the time you get to the capacitors, you're only pulling so many amps. So the last version took actually 3 minutes to charge 1 shot. So it's not very important.
So out of 45 pounds, how much was the capacitor weigh?
20 pounds. So it was mostly capacitors. That's actually one of the things I'm working on in my new design, is bringing the weight of capacitors down. In the version 1, it actually used American capacitors. And those were really heavy, and they're actually not the best you can get. The best bang for your buck is actually Chinese capacitors. They're really, really small, and if you put hundreds of them together, they have a way higher energy density. Yeah?
Do you have a loading system for the projectiles that you're shooting at?
Yes. Yeah. So the old one, it was literally just like a bolt loading thing where you put the thing in and then it loads it into the injector. This new design, essentially the big advancement is it's a semi-auto design. So I have this pneumatic plunger, and yeah, essentially what you have is you have a little carriage that rides along this thing, and you have this specially designed magazine, because there's no part of this armature to grab onto because there's no casing. So essentially what you do is you have this thing, and you jam it in there, and then it locks into place, and then this thing will just cycle. So, yeah. It's not just shoving it down the rails and then firing back out.
And what material is the projectile?
So the projectiles can be anything.
Right.
So a coil gun uses only magnetic synthetic materials. But a railgun, you can fire anything. So tungsten, aluminum, iron, you can fire Teflon, non-conductive stuff, pretty much anything. What's up? Yeah.
What happens if you fire something, some kind of conductive metal through the gun? Like, what does that do to it?
Non-conductive? Or
Yes.
Non-conductive?
Yeah, sorry.
So yeah, if you fire something non-conductive, so the way this design works, this is actually called a plasma armature railgun. It's different than a regular railgun. Essentially, the way this works is it's not actually the projectile that's being accelerated. It's the metal plasma behind it that's pushing the projectile out. And so if you fire something non-conductive, what you need to do is you need to give it some, like a little piece of conductive material. You need to put like a little piece of aluminum foil on the back, or copper foil, or whatever. So there's, that can vaporize, and then the plasma accelerates that out. And I actually validated that it was working like that, and it was actually the plasma that was accelerating that. So, yeah. I could go into kind of some of this, where I think additive manufacturing is going, or...
Go for it.
Okay. So, I guess I'll talk about this a little bit. So, yeah. So, kind of where I think additive manufacturing is going in the future is, this is what we have today. We have, we design a CAD model and then create a mesh, so an STL file, and then we take that STL mesh and we slice it in a G code, and then we take that G code and we make a part. So essentially what you have is you're taking a editable model and you're making it non-editable, and then you take this STL model and you make it platform specific to the hardware you're using, and then you use that hardware specific model to print your thing. So that's where we are today. Where I think we could be going is from an absolute positioning system to a relative positioning system. So biomanufacturing, essentially. And we're already seeing some of this. We're seeing DNA origami, we're seeing magnetotactic bacteria, in other words, a way to get information into a self-assembling system, biobricks, and artificial photosynthesis, all engineered at the molecular level. So where we could be going in the future is, let's say you had a product, something you wanted to make, a whole object, a whole thing. Well, you could make that using something like seeds, or GT seeds. And essentially, you plant those seeds and you water them with the materials that make up your final product. You give them some vitamins, metals, water, and energy, and it self-assembles. So you could do that using something like a system model. You have some differentiation engine, similar to the differentiation engine that's within our cells. It takes DNA and it converts that into differentiated organs and tissues. It's already wanted. Oh yeah. Then you have some sort of a transcription engine that takes that organ model down to a protein model. And then you have G code, some genetic code that's platform specific, and you make these seeds, and the seeds self-assemble. And a lot of this isn't too far off. It sounds way down the road, but a lot of this is way closer than you'd think. There's parts we don't understand. This stuff, we don't understand how to do that. That's a big mystery in biology. We don't understand that part of biology. But this stuff, this is fairly well, we're there. And this, we're getting there faster than you'd think. So this model, it might not be too different from the model we currently have. It might not be too far off. So
the material would have to be elements at that point in time, or
not
maybe
necessarily.
you break it down.
Yeah, I mean, if you're already at the molecular level doing self-assembly, there's not much difference between breaking something down and building something up. Positive versus negative. Add current versus remove current. Add hydrogen ions versus remove them. Yeah. This is where I think. So yeah. Questions? How did we get from homemade railguns to synthetic biology? But yeah, that's pretty much all I have. If anybody has any questions.